I think that's, I can see from there. That seems to be working. Okay, all right. Review time. Okay, so starting with chapter 5. Chapter 5 has force friction and work and pulleys and slopes. So the best way to, I guess, do chapter 5 is just to do throwing everything at once. So we've done this a little bit with some of you. So here is a big heavy box. So it's 2 boxes on top of each other. And mu kinetic is equal to 0.1, and I'm going to say that this mu static is equal to, I don't know, 20 just because I don't want to make them numbers that don't work out. So we're going to say this is 20. This is mu kinetic. So mu kinetic is for all of the boxes and the ground. So here and here and here. While mu static is for specifically the small box and this bigger box. And this is just a really weird hill with an angle of 30 degrees on both sides. So this weighs 10, this weighs 10. Pulley is frictionless and we can completely ignore it, it's no mass. And now this weighs 100 kilograms. Yeah, let's make this 100. And this weighs, I don't know, 1 kilogram, something like that. And actually, you know what? Let's make life easier. Let's make this 99. So this is 99 kilograms. This is 1 kilogram. And yeah, so this is going to be force friction, work, pulleys, slopes, everything. So first of all, whenever you have boxes in contact, just lie and just pretend that this is really 20 kilograms. So if I redraw this, it's really 100 and 20, obviously not drawing to scale. And so now I'm just looking at it from a slope perspective. This is a force gravity. And this will go down with 20 times 9.8 is 196. And this angle here is the same as this angle. So that's 30 degrees. And if you have your calculators and you do trigonometry, so this is, the 196 is right here. It's the hypotenuse. That's the force gravity going straight down towards the center of the earth. Force parallel, which is called force parallel because it goes parallel to the slope. 196 sine 30 will give me 98. And 196 cosine 30 will give me 169.7. So if I take this 20 kilogram box and I take a better look at it, the force gravity was the hypotenuse. So by drawing force parallel and force perpendicular, that they sort of are substitutes for force gravity. So in my more comprehensive free body diagram, I'm not going to draw force gravity anymore. It's gone. So force parallel goes parallel, so I can just take it from here and just put it on the box because that's where it's being applied. And that's force parallel equals 98. And we have a force perpendicular, which is equal to 169.7. And force normal will retaliate against that with 169.7. And then we have a tension force pulling it up. We're assuming, we're going to make a guess that the 100 kilogram is going to pull the 20 kilogram up. 100 is bigger than 20, and I told you it's mu kinetic, so you can assume that it's going to be moving. If they give you mu kinetic and mu static, you would have to check and see if it's even moving in the first place. But it's also a pretty small mu, so it's almost certainly rolling in this direction. So tension, and if this, 20 and these 10s, if they're moving up, friction is trying to pull them down. So force of friction is going down the slope for these. And force friction is equal to force normal times mu. So this force normal is 169.7 times 0.1, which is just 16.97. And this is our 20 kilogram box, which is really just two 10 kilogram boxes smushed together. And so we can work on our some of the forces for this. So I haven't really asked what we're asking for, but that's the point. Regardless of what they're asking for, your approach is going to be the same. They want to know the tension, that's like a normal thing. Maybe the acceleration, we're gonna find both. So if I write out the super formula for forces, sum of the forces is equal to MA. Well, I know that it's moving in this direction. So that means tension is bigger than the combination of these two forces. So for the 20 kilogram unit, tension minus 98, which is the force parallel, minus 16.97, which is the force friction, oriented downwards because the box is moving upwards, is equal to 20 times A. Two variables, I don't know how to solve it, but for pretty much every Atwood problem, every pulley problem, you're going to get the sum of the forces for one thing equals MA, the sum of the forces for the other thing equals MA, and add them together, and the tensions almost always cancel. So we're done with this side, let's look at this side then. So this is 100 kilogram, we're going to do the exact same thing. This is 98, a force parallel. So this is 30 degrees. So this gives me 49. The force perpendicular is 85. I just memorized those, but you would do trigonometry to figure that out. And so this is ugly, and anytime it starts to get ugly, I'm gonna redraw it so it's neater. So here's my big 100 kilogram box. And remember, the 100 kilogram is really just a 99 and a 1. And it has a force parallel going downwards. The force parallel going down is 49. The tension is going to pull it the other direction. And this tension should be the equal and opposite of this tension. That's Newton's third law. That is always the case when you have tensions pulling on things. And if it's sliding down, we should have a force friction moving upwards. Force friction. Let's not forget our force perpendicular, which is 85. Our force normal, retaliating, which is also 85. And the 85 and the 85 in the perpendicular direction cancel out. I'm only concerned in the parallel, anti-parallel direction, just like earlier. So, we're assuming that it is going down. Also, nobody corrected me on this. So it's not 49, it's 490. I was about to say, that seemed really small. You were thinking it the whole time. Yeah, so this is 490. Otherwise it seemed way too small that it's just 49 pulling this down. So that's 100 times 9.8 is 490, which means this is 850, 850, 850. Quick correction. All right, so the 490 minus tension minus the force friction is the sum of the forces. So if we write that in here, it's 490 minus the tension minus the force friction. We didn't calculate the force friction yet. The force friction will be the force normal, 850 times mu, which is 0.1, which is 85. 85. So 490 minus t minus 85 is equal to 100 times A. And look what happened every single time. So positive t and minus t cancel. And I get 490 minus 98 minus 16.97 minus 85. And what is all that? Minus 98 minus 16.97 minus 85 gives me 290 is equal to 120A. 290 divided by 120, 2.4167 is equal to A. Okay, cool. So both of these are accelerating up with 2.4167. Both of these are accelerating down with 2.4167. And that really incorporated pretty much everything. There is one more thing I want to focus on. It's a really common, like a little trick question at the end. So we did all of this work. So their ultimate question is, what is the force friction between the 1 kilogram and the 99 kilogram box? So I'm going to draw the free body diagram for this 1 kilogram thing. So this is a 1 kilogram. It's in contact with this bigger thing, which is on the hill. So the force of gravity for this is 9.8, which also gets broken up into the 30-degree, force parallel. Force parallel is 4.9. Trigonometry will tell you this. Force perpendicular is 8.5. Force normal is 8.5. And so I'm gonna draw, so this 1 kilogram, I'm gonna draw one more time over here, make it a little bit neater. So this is 1. It is a force parallel equal to 4.9. And, a force perpendicular, 8.5, a force normal, 8.5. I really don't care about those, they cancel out. So question to you guys, which direction does force friction have to act? It's going up, right? Because otherwise it would just slide right down off of the box. So force friction has to go up. And we can calculate force friction. Force friction is just the force normal, 8.5, times, in this case, 20. So this is force friction is equal to 8.5 times 20, gives me 8.5 times 20 is 170. Okay, that will be one of the answers. So it's multiple choice, A, B, C, D. One of them will say 170. That's absolutely not the right answer for this 1 kilogram box. Why not? It's a maximum. This force friction static is a maximum value. That's why this is in US. So it can get to 170. But if this was 170 and this was 4.9, that means this whole thing would be sliding down and this would shoot up into the sky, which would be really, really, really weird. So in actuality, this is 4.9 going down, and we would want to balance it out with let's see. We want to make sure that the sum of the forces, 4.9 minus the force friction, is equal to the mass 1. What's the acceleration of the 1 kilogram box? It's the same as this whole thing. It's 2.4167. So it's equal to 1 times 2.4167. And 4.9 minus 2.4167 gives me 2.483. So the force of friction is equal to 2.483. So obviously Adler doesn't ask problems that, does that make sense?
Yeah, I just thought at the beginning you said they're asking for tension.
Oh, okay, yeah. I don't even remember what they're asking for. So they're asking for two things. They're asking for tension and they're asking for force friction. Well, easy. How do we get tension? I can just plug this acceleration into here, or I could plug it into there, and then you get tension. Yeah. So the whole point of this is obviously Adler's not going to ask a question that's so number intensive, that's this long, but this is inclusive of every possible tool you would need to solve problems. Adler's going to ask a stupid problem like, you have this whole thing set up, and then you double one of the masses. What happens to the acceleration? When he gives you that, make up numbers, plug them in, and then plug in the new numbers, and just see what the new values come out to be, and you will realize that you'll come up with the answers quicker. Like a quick question he could have said is, he could have said, okay, you have mass M, mass 99 M, mass 0.1 M, or maybe he gave you even like the forces. If he gave you this entire thing, and he said that the whole thing is descending to the right at a constant velocity. So I take back the M. So this is 1 kilogram. They could say, what's the force friction of the 1 kilogram box? Well, you would have wasted a lot of time if you did all of this. Because you would realize, okay, well, the force of gravity of this is 9.8, which means the force parallel is 4.9. Now, if it's moving down at a constant velocity, that means there's no acceleration in the parallel direction. In that case, 4.9 minus the force friction is equal to 1 times 0. Force of friction is equal to 4.9. And then maybe you could have figured out mu or something like that. That's the type of question he'll ask. It's just a quick conceptual, you don't have to do a bunch of math type question. Question there?
Yeah, I don't understand what you.
Sure. So if I have a slope and I have both of these boxes are descending at a constant velocity. If I just look at the top box is also descending at a constant velocity with the bottom box. Well, the parallel and anti-parallel forces on this, there is a force parallel on the top box due to its 1 kilogram. And we would calculate using all the traditional methods that it's 4.9. It's 4.9 directed down the slope. But there's friction as well. And friction will pull it up the slope. The friction automatically, that's a 4.9, automatically has to match the force parallel if there's no acceleration.
Oh, because if you put it in the equation again, that times MAA would have been 0.
Exactly. And so it's actually the same whether the whole thing is sliding down, the whole thing is being pulled up, or it's just stationary. All of those would have been essentially the same thing. And okay, so that's chapter. Yeah, question.
I have 2 questions.
Sure.
When it comes to the force parallel, how do you know which way to put it? Is it just opposite of force?
When it comes to force parallel.
Yeah, so when you have the weight, when you calculate mass times gravity, and then you're trying to split it up into force perpendicular and force parallel,
Sure.
how do you know which side to put force parallel on?
So if I'm looking at this, so the force gravity is going straight down towards the bottom of the earth, down there. So this is my force gravity. You draw one line that is exactly perpendicular to the page, to the plane, and then one line that is parallel to the plane. And there you have it. The one that goes perpendicular to the plane is your force perpendicular. The other one is the force parallel. Because it literally goes parallel.
Yeah,
with
and then how do you know whether it's the force parallel is going like
Up or down?
up or down?
The force parallel. The force parallel will always bring it. The force parallel is bringing these down, and it is also bringing this down.
Because it's part of gravity.
Yeah, so gravity is only going to bring
Oh,
this
so
guy
it's just-
down.
oh, okay,
It's the
okay.
tension that's pulling it up.
Oh, okay.
So gravity pulls this down. So gravity's pulling this down. Tension's pulling this up. Friction's pulling this up. But it's just that the gravitational parallel component of this overrides the tension and force friction. On the other hand, force parallel pulls these down, and the combined tension pulls them up, and the force friction pulls them down. But it doesn't matter. The tension in this case is bigger than the parallel and the frictional force. And again, he's not going to ask this verbatim
Yeah,
question, but this
perfect.
includes everything you would have to know, except for force centripetal, which I almost forgot about. So let's do a really quick force centripetal problem, because I want to get to energy and then momentum, and then any questions you guys might have. Actually, any other questions on that? I mean, I know that was a lot, and we went really, really, really quickly, but that's also why we're taping it, so you can just review the tape and ask any questions. So, I have a car. It's going on like a really hilly road, and I want to know. So the car weighs. Do they even need to give you? I guess they don't need to give you that. No, they don't need to give you that. I have a car, mass M. I don't know if it's like a Prius or if it's like a pickup truck. It's mass M, and the hill that we're on has like a radius of 50 meters. I guess all of these hills are all the same. 50 meters. And I want to know, so I'm asking 2 questions. I'm asking 3 questions. I want to know the force normal here and the force normal here if my velocity is 20 kilograms. And I guess if I'm asking the question this way, we need to have this car weighs 1,000 kilograms. So yeah, I'm changing the question, so I need to give you more information. So car is going around this hill, I want to know what's the force normal at the top. Anytime you see that you're going in any sort of like circle or half circle, it's centripetal motion. It's a constant velocity from here at least. And we know that the centripetal force, which is the net force, so it's not any real force, it's just a sum of other forces, is always directed towards the center. So towards the center, like towards the center basically, towards the center. So we focus at this point here. The force centripetal, so it's the sum of the forces is equal to the force centripetal equals, instead of ma, mv squared over r. So it is very similar to our super formula from chapters 4 and 5. So right here, the sum of the forces, force gravity, old reliable, pulls you straight down. So it's force gravity plus force normal is going in the same direction as the alleged centripetal net force. So that is 1,000 times 9.8 is 9,800 plus force normal is equal to m, 1,000 times v, 20 meters per second squared over the radius. The radius is 50. And we're just going to solve for force normal. So I take that back. This is different than in the previous problems. So we've been doing Hot Wheels problems. So I'm mixing this up with a Hot Wheels problem, which is actually a really interesting point. In this case, when the Hot Wheels hangs on the inside of the car, in this case, the force gravity and the force normal both point down. Force normal is the ground. The ground can never pull on something. You can only push on something. So I did with most of you guys this Hot Wheel problem. So here, the force gravity goes down and the force normal goes up. Here, the force normal goes to the left even. Force gravity still goes straight down. And at the top, they both push down. But if I'm driving like a normal human being, not in like a Hot Wheels super loop, and I'm here, the force normal doesn't pull me into the center of the earth. It's just the ground pushing up on me. So this was an incorrect way of drawing it, completely by mistake, but it does highlight an important point. You need to know damn sure which direction your force normal is going. And it is always going to, like a tension will pull. But if it's the ground, it's going to push on me. If I punch the board, force normal is that way. I'm not going to punch the board and have force normal pull me into the board. It's going to retaliate. So if I'm on top, the ground's pushing up. If I am going around the track, like inside of the loop, the force normal is still pushing down. So if I could walk on the ceiling, the force normal would push me down. Okay, so resetting this up then, force gravity goes in the same direction as the centripetal force. Force normal goes in the opposite, which means it's a minus. And let's see what this gives. 9,800. So 1,000 is 20 squared divided by 50. So this is 9,800 minus 8,000. I'm getting 1,800 is equal to the force normal. So the force normal here is 1,800. So that's part 1 of 3. So next I just want to know what's the force normal at the bottom here. So it looks pretty similar. Force normal goes up, force gravity goes down, but where's force centripetal going in this direction? Now it's going up, it was going down. So now I'm just going to rewrite this slightly to be force normal, whatever the heck it is, minus force gravity. So instead of force gravity minus force normal, we have force normal minus force gravity, which again is a different scenario than we see in these roller coaster hoop-de-loop problems. Equals 1,000 times 20 squared over 50. This is 8,000. This is 9,000. So this is 8,000 plus 9,800 is 17,800. Force normal is bigger at the bottom, and that is almost always the case. Your force normal at the bottom of a loop is always bigger than at the top of the loop. If you go on a roller coaster, you're going to feel heavier at the bottom. If you're going in like a crazy European road trip, you're going to feel heavier at this and light at this. And the last and probably most important part is if you go fast enough, anyone who's watched like a Fast and the Furious movie knows you're going to go flying over the edge. So I want to know what is the minimum velocity I need to fly off the edge of this, so the car gets like airborne, basically. And this is similar to, for most of you, the problem I did with the Hot Wheels car going and what's the minimum velocity, just barely make it around the loop. It's the same basic idea. So when we did this, and I said, what is the minimum velocity to barely make it around the loop? I explained that barely making it around the loop means that the force normal is now 0. It is ignored. And what's the same thing here? If I am airborne, I am no longer touching the ground, which means my force normal, it does not exist. The ground cannot retaliate if I'm not touching it. So right at this point here, right where I'm just beginning to go airborne, I only have a force gravity, and my force normal is now equal to 0, or 0.0001 if it helps. It's just where we're just beginning to go airborne. Okay, well in that case, force centripetal goes down towards the center of the circle. Force centripetal goes up towards the center of the circle. Force centripetal goes down towards the center of the circle. Again, force centripetal, not a real thing. It's just describing the direction of the net force. In this case, the force centripetal is equal to the force gravity minus force normal, which is just 0. So force centripetal equals force gravity. And this is mv squared over r is equal to mg. And you could cancel this and move this around. And you would get that the velocity is equal to the square root of rg, which I think is a formula that you guys have. But again, I think it's important to know where the formula comes from. So this is equal to the square root of 50 times 9.8. 50 times 9.8, square root of that. So if we go with a velocity equal to 22 meters per second, we will go airborne. We almost went airborne here, right? The faster and faster we go, the smaller and smaller and smaller force normal will be at the top, and then eventually we will just lose force normal and be airborne. So that's a pretty good centripetal force problem that you'll see a lot of questions like that. Questions on this? Okay. Does anyone have the time?
9 o'clock.
9 o'clock. Okay, cool. We're doing okay on time. We might not have time for as many like after-thought questions as I wanted, but all right. So energy. Energy problems all kind of go together. Let's see. We have a box. It weighs 10 kilograms. This box weighs 20 kilograms. And mu kinetic is equal to 0.1 kilogram, and yeah, let's just go with that. So I'm telling you that this is moving. Actually, you know what? You would know this is moving because of what I'm about to say. About what I'm about to say. Oh my gosh. So this falls from 100 meters to 99 meters. And it starts out from rest, the velocity initial 0. It makes this fall in 2 seconds. And actually no, I guess I don't even want to give you that. Actually no, I do want to give you that. 2 equals 2 seconds. And I actually take this back. Okay, so I want to know mu. That's my question. What is mu? Yeah. Happy with it. Well, first of all, you know, this is going down 1 meter. That means this is going to the right 1 meter. So this is going to the right 1 meter. And this problem, a lot of these energy problems, you could solve using Newtonian mechanics. So if you really wanted to, you could easily solve this with Newtonian mechanics. Again, this is not exactly what an Adler problem will look like, but it'll be the similar scenario, and all the theoretical components are the same. So my super formula for chapters 6 and 7 is mechanical energy plus work equals mechanical energy final. Work is, there's two definitions of work. There's the sucky definition, which is like if a basketball that weighs 1 kilogram falls 1 meter, what is the work done by gravity? In this case, I would say, okay, well, the force of gravity is just equal to 9.8, and it falls 1 meter, and I know that work is equal to force times distance. So that's the force of gravity, 9.8, times 1 equals 9.8 joules. Gravity did 9.8 joules to this. And yes, that's a sucky definition, but it's still one you have to know. So here I'm just defining work as any force that, acts for a certain distance. But this is a bad way of thinking about it, I think. And even the mastering physics problems kind of was ambivalent about which definition of work you want to go by. So understand what he means if he specifically asks for what is the work done by this? Well, you just take that force and you multiply it by the distance. But what's important is for our formula, and this isn't just my formula, this is pretty similar to the book formula. When they say work, they don't mean this work. So you need to go to what I think is the better understanding of work, where work is transfer of energy into a system or out of a system. And there was already 9.8 joules of potential energy converted into 9.8 joules of kinetic energy. No external energy was added, so that this 9.8 does not go up here. This is only work transferred into a system by chemical energy. Chemical energy is people pushing things, or it is things exploding, and energy work that makes energy leave a system is just, for the most part, frictional energy. So back to this rant over, we think work not as this, though you need to understand this, work is energy entering or leaving our system, which is friction or chemical energy. Okay, so initially, what is our mechanical energy here? Well, nothing's moving, so we don't have any kinetic energy. This box is on the table, so there's no potential energy here. We only have gravitational energy here. It's potential energy. So I'm going to write the gravitational potential energy as our initial mechanical energy. Mechanical energy being kinetic, gravitational, and elastic energy. Now it's 100 meters. So I could say that it's 20 times 9.8 times 100, but that's more work than you want to do. So if you know that something goes from 100 meters to 99 meters, and in most cases, honestly, just pretend like it goes from 1 meter to 0 meters. You will get the same result with less work. You don't have to include that 99, height of gravitational potential energy over here. So I'm just going to say times 1, and pretend, oh, you know what? This is 1, and this is 0. It hits the ground, because it would be the exact same whether you assume that or not. And remember that Adler can do the reverse. So he can be annoying, and he could say that a baseball falling from a meter of 1 to a height of 0, he could just say, okay, say that this height is equal to 5. Or say that the ground level is equal to 5. That means, so if I redid that, if he said, say that the ground level is equal to 5, and I know that this is 1 meter above, you are forced to, if he stipulates in the problem, saying that the height of the baseball is equal to 6, and the height of the ground is equal to 5, and you would get the same answer. So that's just what we did in reverse. So this is stupid that he might have you do it. This is the smart thing. If they give you 199, you just say 1 and 0. So back to our energy considerations. We only have gravitational potential energy. It's just 20 times 1 times 9.8 plus the work. So what is the work in this problem? There's no work here. There's no chemical energy, but there's friction in the ground. So we're going to lose some energy. We're going to have less final energy than initial energy. So work due to friction is equal to the mechanical energy final. Well, if this moves 1 meter to the right, it's still on the table, so there's no gravitational potential energy here. Now we're pretending that this hits the ground, in which case there is no gravitational. So there's no gravitational here or here, so that's for gravitational. But there's kinetic. This is 1/2 mass velocity squared, 20 v squared. This is also moving with the same velocity. They have to be moving together. So this is also 1/2 mass 10 times the velocity squared. And I believe those are the only types of energy we have. But I know I can figure out V. I gave you the T, right? So you're gonna have to pull in a lot of like older stuff now. We know that T is equal to 2 seconds, and the initial velocity is equal to 0, and the delta y is equal to 1, and we can solve for that. I can say that delta y equals VIT plus 1/2 AT squared. That is still important, and you have to know it for this exam. This is equal to 0 times 2 plus 1/2. Oh, actually, you know what? Why am I even doing that one? That would give me the acceleration, which I don't want. I would want the acceleration if I was doing forces, but we're looking for the final velocity, in which case it's V final equals V initial plus acceleration time. Wait a second. V final equals... We might have to do it the other way first. V final equals... It's very weird. Okay, that's fine. We have to do it the other way. So we're going to say that the 1 is equal to the initial velocity plus 1/2 times the acceleration times time squared, which is 4. That's 1 equals 2a. So acceleration is 0.5. 0.5 is the acceleration. So V final is now equal to, so I'm just plugging that in here. So V final is equal to 0 plus 2 times 0.5. V final is equal to 1 meter per second, which works out pretty nicely. Does that make sense?
Yeah, I couldn't really see what you're doing.
Okay, so I just forgot. I thought we could like immediately find the final velocity, and I was going through the formulas in my head, and I guess we couldn't. We had to find the acceleration first. So we have the time, the initial velocity, and the delta y. So I just plugged it into delta y equals VIT plus 1/2 AT squared, and that gave me the acceleration. That acceleration was 0.5. Now that I have the acceleration, I can plug it into the third of our kinematics formulas. V final equals V initial plus acceleration times time, and that gave me the V final, which is 1. Now that I have the V final, I can plug it back in over here. And so 20 times 9.8 is 196 plus the work of friction is equal to 1/2 of 20 times 1 squared is just 10 plus 1/2 times 10 times 1 squared is just 5. And I get that the work is negative 181 joules. But that's not the answer. They're asking for mu. So mu, or work, is equal to force times distance. This is an okay definition of work because it's taking energy out of our system. So I'm okay with this being this, and it also simultaneously being equal to force times distance, as opposed to that stupid work done by gravity, because that energy was there before and after, as opposed to this is energy lost. So force times distance, the force is the force of friction, and the force of friction is just force normal times mu times d. So force normal times mu times d is negative 181, or we can just say 181. The negative is just telling us that it's moving to the left. So 181, the force normal is, gravity is 98, force normal is 98, so it's 98 times mu. And if this went down 1 meter, that went to the right 1 meter. So it acted for 1 meter is equal to 181. And mu is equal to 181 divided by 98, 1.85, which is pretty big as far as mu's go. But I made up these numbers, so it's going to be a little bigger than normal. So to recap, we could have solved this with Newtonian mechanics, but we didn't. We used our super formula. Mechanical energy plus work equals mechanical energy final. I noticed there's no kinetic or potential energy here, there's no kinetic energy here, but there is potential energy here. That potential energy is mgh. And 100 meters to 99 meters, we might as well say that the height is 1 meter. We have friction, which takes some of our kinetic energy and it dissipates it into the environment as heat. So I need to include this, and I'm expecting that's a negative value at the end of the day, because it is taking energy out of our system. This is equal to the mechanical energy final. Well, this is hitting the ground, allegedly, so there is no gravitational potential energy. But right as it's hitting the ground, it has a velocity. So I have 1/2 the mass velocity squared the kinetic energy. Same thing for this. This doesn't have a height, but it still has a kinetic energy, so I include that as our 1/2 mass 10 velocity squared. And this has the same with the same velocity as this, otherwise the rope is going to stretch or compress or something which we are not allowed to have. And we can figure out the velocity with old kinematics formulas. So we know that the height was 1 meter and the time was 2 seconds, and the 1 meter, and the initial velocity is 0. You have 3 variables. All of the kinematics formulas have 4 variables. You can just kind of plug in for stuff. And you probably could have done it a different route than I did, but just somehow you can plug it into one of those 3 formulas, which you'll still get on the exam, and you can solve for the final velocity being 1 meter per second. We plug that in over here. We solve for work friction. That's negative 181. Work is also equal to force friction times distance. And force friction is equal to force normal times mu, then times distance. So I have 181 is equal to the distance, which is 1, and the force normal, which is 98, and I solve for mu is 1.85. That is energy in a nutshell, though we'll look at momentum, again, incorporates a lot of this stuff. It is very cumulative. Is there any questions on this? Okay. All right, so I've done this with some of you, but I just think it's a really good practice. There was a lot of mastering physics homework questions about it, and it just, it really helps you understand how to relate all of the formulas for everything. And it's very Adler-esque. So the problems I've been doing have not been so Adler-esque, but it's still, physics concept is a physics concept. So I have a toy car of mass m. It has a tiny electrical engine with some force, and that force propels the car for 1 meter. Delta x equal to 1 meter. I want to know if I keep the same engine, but I change my car so that it's now a mass of 2m. I want to know what is the momentum. Or how do the momentums compare? How do the velocities compare? How do the kinetic energies compare? How does the time to reach that 1 meter destination, how does that compare? How does the work compare? How does the impulse compare? There's probably one more question I could ask. Kinetic energy, that work, impulse, momentum. I feel like I'm forgetting one. Any thoughts?
But you included this displacement here, so I think that's it.
Yeah, I guess that is it. Okay. And great. So I'm just gonna, he says you double the mass. Well, you know what? That's just a car that weighs 2m, and it has the same engine, so it has the same force propelling it, and it's also going 1 meter. So this is how you should draw up this problem. And on the homework, and what he could do on the exam, is instead of saying it goes a distance of 1 meter, he could say it goes for a time of 1 second. And you would still approach it essentially the same way. And so yeah, we're gonna solve it this way. So our formulas, to recap all of our formulas, mechanical energy initial plus work is equal to mechanical energy final. Work can alternatively be expressed as FD. FD cosine theta, but normally no one cares about the theta because the work is in the same direction as the displacement. If it's in the opposite, work is negative. If it's in a perpendicular angle, there is no work because cosine of 90 is equal to 0. If it is at a weird angle, then you just solve for the component that's going in the same direction, which is generally just going to be FD cosine of that weird angle. So this is one formula. This is technically 2 formulas. And impulse. Impulse is J. J is equal to a change in momentum, and a change in momentum is equal to force times time. So we have 3 formulas. Let's say Formula 1, Formula 2, and Formula 3, which all kind of help for these momentum-esque problems. Are we on time? Good on time. Okay, so he does this all the time on his exams. He gives you these BS mass, force, values, and then you can't really deal with numbers, and it's not very tangible. So make up numbers. If he tells you mass, say, oh, you mean mass 10 kilograms and mass 20 kilograms? Because for all I know, M is 10. And if he says force, if it's the same force, why not say that force is also 10? And now I have enough to actually really solve for something. So I want to think of the variables that I have. I know that the force is 10, mass 1 is 10, mass 2 is 20, and actually, you know what? It might actually help to make a table. So these are things that they both have in common. So this is 1, this is 2. Mass is equal to 10 for the first one, and mass is equal to 20 here. And they both have a displacement, delta x, of 1 meter. Okay, so right off the bat, I have F and I have delta x. Delta x is d. F times d is work. That was just, I probably could have gone somewhere else, but that's just immediately, I'm seeing what numbers do I have, how do they fit into my formulas? And so that's great. I know that the work is just 10 times 1. There's 10 joules of work done. They both have the same engine. So that's both 10 newtons times 1. It doesn't matter whether I'm talking about the small car or the big car. Okay, well, the initial velocity is, I suppose we also know the initial velocity, starts from rest. And if they don't tell you it starts from rest, assume it starts from rest. If it starts from the rest, mechanical energy plus work equals mechanical energy final. Starting from rest means there's no height, there's no spring. All I would ever have here is kinetic energy. And if it's not moving, I don't have any kinetic energy. Kinetic energy is 0, which means that the work is just equal to the mechanical energy final, which again, there's no height, there's no spring, so it is just kinetic energy. Work is equal to kinetic energy. So I know that the kinetic energy is also 10 joules. So right off the bat, whatever the question says, you have car mass m, car mass 2m, they have the same engine, they have the same force. Their work and kinetic energy are not 10 joules, we made up most of these numbers, but I know that they're equal. And that's the important bit. That's how you solve these stupid, untangible Adler problems where it just gives you variables. You counter that by making up variables, and this will go all the way on to the last day of physics 2. Okay, so coming back in here, so I know the kinetic energy is the same as the work, which is 10 joules. So this is 10, and kinetic energy is to 1/2 the mass times the velocity squared. Well, the mass is 10 for the small one times the velocity squared. And so 10 equals 1/2. 10 squared is the square root of 2, is the velocity here. So for this one, the velocity is equal to square root of 2 at the finish line. Velocity equals square root of 2. And for the other one, 10 equals 1/2 times 20v squared. And now that the square root of 1 is 1, 1 is equal to the velocity. So here, velocity final at the 1 meter finish line is equal to 1. And we should have been able to predict that. So we're doing a lot of work here, and it'll help you if you can predict what the answer will be. If I have two things and I apply the same force to them, one of them is a lot lighter, you know, at the end of the day, I know F equals ma. Same force, smaller mass means a bigger acceleration. The smaller thing will accelerate, move faster. It'll reach the finish line quicker. It'll be moving faster at the finish line. And all of our numbers should kind of represent that. Some things like what's the impulse might be harder to conceptually guess, but it should make sense that this one reaches quicker, this one reaches in a longer time. But we're making up numbers, so I'm not even leaving, I just want intuition to confirm, yes, this checks out. And again, your answers will not be so easy, it won't be root 2 and 1, but you'll say that velocity, like small, is equal to root 2 velocity big. Something like that. Or velocity big is equal to v small over root 2. That's again how the answers will look. I think that's stupid, but you're just comparing these for the answers. Okay, so we're almost done. What's the what is the what's the final momentum? Well, momentum P is just equal to m times v. So I guess that's another formula. P is equal to m times v. So that's our fourth formula. M times v. Everybody should know that. P is momentum. It's a weird letter. J is impulse. It's a weird letter, but that's just what they are. So this is equal to 10, my mass, times my velocity. Root 2 is like 1.4-ish, just so we can have 1.41. So my momentum is equal to 14.1. For the big guy, for the small guy, what about for the big guy? Momentum here is equal to, I said 20, right? 20 times my final velocity at this point, which is just 1. So my momentum here is 20. The bigger thing has a bigger momentum. And again, it won't be 20 and 14.1, but it'll be momentum big is equal to momentum small times root 2 or something like that, or times 1.41, which is root 2. Okay, so that's we got the momentum. That's done. That's done. That's done. That's done. The impulse. Okay, impulse is just a change in momentum. We started off with an initial velocity of 0, so the change in momentum is just momentum final minus momentum initial. Well, momentum initial, if you're starting from rest, is 0. So change in momentum, which is impulse, is just our momentum final in this case, because we have no initial momentum. And so the impulse is also 14.1 and 20. And then the very last thing to compare is the time. Well, impulse is equal to change in momentum, which is equal to force times time. So this is 14.1 is equal to force times time. And I'm predicting this should have a smaller time. Let's see if that checks out. Our force, we said right from the get-go, was just 10. We just made that up. We said, okay, the force is 10. That means the time is 1.41 is equal to here. And this time should be 20, our impulse, is equal to force times time, which is, the force is, force is 10 times time, and 2 is equal to t. Again, that checks out. We predicted that. The t is 2, the t is 1.41, and that's 6 variables we just solved for. Again, they could do something, I can easily see this being on the test. Maybe they give you a different variable instead of the other variable. It doesn't matter. Keep, what they have in common. This is 1 and 2. This is just 1, this is just 2, and then you're just kind of solving for variables using these formulas. Moving in like random directions. Just where can I just plug in something? Where does it fit? If I can plug in something, boom, I got an answer. I'll plug in to get something else. I could not have gone from the very beginning to find the time, right? So let's say that this question was car mass m, car mass 2m. I want to know the time. How does the time compare for both of them? If you went right away and said just J equals delta P equals FT, it would have been really difficult because we had to do a lot of things before we solved for the time. I'm just kind of randomly solving for things in this case. I suppose if we were looking at this initially, I would have said the change in momentum is the force times the time. And I know the force, I don't know the time. Well, the change in momentum I know is P final minus P initial. And then you should have realized that P initial is 0. And so essentially here we just have P final is equal to force times time. And then P, I just know is m times v is equal to force times time. And the force was 100. So let's say I'm looking at this one. The force was 100. The mass is 10 times v. So I know I'm solving for t. That means I have to find v first. So now I have to think about what are ways I can find v. And then I need to kind of access the rest of the formula. Figure out, okay, I have F and D. That gives me work. Work gives me kinetic energy. Kinetic energy gives me 1/2 mass velocity squared. Velocity then comes in here, and then I can get the t at the end of the day. So it is better to just kind of solve for whatever you can solve for. It's not going to take that long to solve for everything, go for the time. Anyways, we got to keep going. Let's do one more. Actually, let's do 2 more problems. So I don't even know if we would get to questions. Yeah.
Okay, just like for an example with the time, when you have that the small car is 1.4 seconds and the
Sure.
large is 2 seconds, What's the easiest way to compare it? Like if it says like time of small equals 1/2 time of,
I would look at the answers, and if you see a root 2, then I wouldn't have converted to 14.1. I would have just said it was, I think, what did we say? We said it was 10 root 2 or something. I would have just said it's 10 root 2, and then I would have said that the time of the small is the time of the big over root 2.
okay.
And if you have numbers, I agree, sometimes it's hard. You say it's twice as big or twice as small. Just plug them into whatever the answer says.
Okay.
And if it's a true statement, then you did it correctly.
Okay.
That's what I would do, because I easily get tongue-tied with that too. And if you plug it in with real hard numbers, it'll tell you the truth. Okay, so here we have a rocket ship. Okay, so there's a conservation of momentum in the x direction versus the y direction. And so this thing, goes up in the sky. It weighs 100 kilograms, and then it blows up into mass m and mass 3m. But it blows up at its max height. Now, this max height is 1,000 meters high. And mass m goes flying to the right, and mass m goes flying to the left. And I want to know a bunch of things. Let's say that mass m lands 1,000 meters to the right of where the rocket lifted off. And so I want to know how far away did the 3m go to the left? Well, first of all, I only do this. This is an exact problem from a test. Mass m is just 25. Mass 3m is just 75. So let's cut that shit out right away. So 25 to the right, 75 kilograms goes to the left. And it was at its max height, which means v is equal to 0 at the very top. Okay, so v is equal to 0, and great, so it explodes. So for momentum, something's a collision when things collide. It's obvious, it's in the name. But here, this is another form of collision. An explosion is a collision. So all collisions are elastic, which are conservation of kinetic energy and conservation of momentum, or inelastic, which is just a conservation of only momentum. Momentum is always conserved. So they had that stupid problem in the Mastering Physics that says sometimes momentum is not conserved, but that's talking about momentum of one thing. If you talk about momentum of the system, it's always conserved, which if you don't know what I'm talking about, ignore it, but that was something that bothered me in the homework. So conservation of momentum in the x, conservation of momentum in the y, and so in the y direction, so if things stick together, it's inelastic, and kinetic energy is not conserved. Generally, you lose energy if it sticks together. If it's an explosion, it's still inelastic, kinetic energy is not conserved. But in that case, usually you gain kinetic energy. Chemical energy from the explosion becomes kinetic energy. It's transferred into it. So right before the explosion, in the y direction, so momentum before is equal to momentum after. Right before the explosion, in the y direction, my momentum is 100, my mass, times 0. We went to our max height. At our max height, we no longer have a velocity, not in the y direction. So this is equal to now 25 times 0 plus 75 times 0, and that does not yield any interesting information. Depending on the problem could have been harder. Maybe it would have been relevant. It just depends. But you still want to think about the y versus the x. So now in the x direction, conservation of x momentum, we have 100 times 0. It's still 0. Because it wasn't moving to the left or the right before it exploded. It went just like this. And and then it blew up. Some of it went to the left, some of it went to the right. So this is equal to 25 times, I'm going to assume, well, 25 is going to be positive, so I'm going to say V. And 75 is probably going to be negative, VB. But I'm just still going to say VB. It'll come out negative on its own. So I don't need to say negative VB, because I already know it's probably going to be negative. It'll work itself out. And so I have two variables, and shoot, it's the end of the day, I should go home. No, we can go back to kinematics. So kinematics, really, this is a very cumulative chapter. This is a height of 1,000. So I have an X and a Y values. Here, delta Y is equal to 1,000. Acceleration is 9.8 going down. The V initial is equal to 0. So yeah, the V initial is 0 because it's only going to the left. Also, it'll say they hit the ground at the same time. That's sort of your clue that it doesn't explode and one of them doesn't go higher than the other, because then one would hit the ground and then the other would hit the ground. But here, if they hit the ground at the same time, neither of them had a Y velocity component. Okay, so now with these I can solve for the time. The delta Y is 1,000 is equal to 0 VIT plus 1/2 AT squared. So 9.8 times 1/2 times T squared. And I solve for this. So 1,000 divided by 4.9, square root of that, 14.29. T equals 14.29. Okay, that's awesome. I'm curious, I hope this thing's still going. That would really suck. Still going, all right. I bet it's screwed up. Did I? No, we're good. Okay. 14.9. So this went 14.9 meters per second. But if they hit the ground at the same time, this one is also 14.9 meters per second. And I want to know the final, wait, no, do I? Oh, sorry, so that is true, but I want to know, I know that this is a delta X equal to 1,000. I'm not quite done yet. I want to know what's the initial velocity for this 25 kilogram thing to the right. Well, I know that the displacement is 1,000, but the acceleration is 0. Hey Yash, will you give me like 10 minutes? I'm running a little bit behind with the physics people.
Okay.
All right, thanks man. So A is 0, T is equal to 14.29, and yeah, that's it, that's enough. So for this, I can say that, okay, it takes 14.29 seconds to basically just fall to the ground. So that's how long it must be traveling to the right. And it goes 1,000 meters in that time, and I can just say that delta X is 1,000 is equal to my initial velocity times my time, 14.29. And the acceleration in the X direction, nothing. There's almost never acceleration in the X direction. There was a quick acceleration here when it exploded, but here there's no acceleration. And I'm going to solve for that to get 70. My rocket goes up, it explodes. The 25 kilogram thing moves to the right at 70 meters per second and eventually lands after 14.29 seconds. That means this thing goes up, explodes, and lands after 14.29 seconds. And I want to know what its velocity is. What is velocity B? Well, I just figured out this velocity, the 25 thing, goes 70. So it's not such a mystery anymore. And I get negative 25 times 70 is equal to 75 times VB, and negative 25 times 70 divided by 75, negative 23.33 is equal to VB. I mean, they could ask all sorts of things. They could say, how far does the 75 kilogram thing go to the left? Well, that's easy. It's just this number times 14 point, that shouldn't be 9, that should be 29, 14.29 to the left. You could give the displacement, and you could add them to find the distance in between them. There's a bunch of silly ways of asking pretty much the same theoretical questions. The big idea is that the conservation of momentum in the y direction is conserved, and in the x direction is conserved. And we're not forgetting about kinematics, so we might have to go and use kinematics to solve for things like the time and the velocity. And yeah, this was on one of my exams. I've seen it on a practice exam. It's a common type of question. It can be asked differently, but like a cannonball is shot out of the air and explodes at the max height. Lots of questions like this. I'm gonna look for old exams to send y'all. I do want to actually do one more question. Do you question?
What is negative 23 point?
That is the velocity that the 75 kilogram thing moves to the left with.
Okay, and how do we know it's moving to the left?
So let's say it was moving to the right. What was my momentum in the x direction before the collision?
None.
None, right? So if they're both moving to the right, that means I have momentum is a vector. That means I have momentum moving only to the right. Well, that means 0 is not equal to some momentum to the right.
Okay.
So your momentum to the right, due to the 25 mv, has to cancel out. So that's where 0 equals this momentum plus this momentum. They have to cancel out. One of them has to be negative. The 75 kilograms momentum to the left direction. Also, they could have asked for how much energy was stored in the explosion. What was the kinetic energy right before the explosion? 1/2 mv squared, and it wasn't moving in the y direction, and it wasn't moving in the x direction. So 0 kinetic energy right before the explosion. Right after the explosion, my kinetic energy is equal to 1/2 25 times 70 squared plus 1/2 times 75 times negative 23.33 squared. Notice a negative value squared, which is positive, so kinetic energy doesn't really care about directionality. So whatever this kinetic energy is, I don't know what the math is, let's say it's 10,000 joules. Where did that 10,000 joules come from? It came from the explosion. That was the energy added to the system due to the chemical energy and the explosive material inside of the rocket. Okay, going to erase this in a second and do a hanging block problem. And so yeah, some of you guys told me that you had questions, so just text me any questions that you have if you can't figure them out, and I will get back to you. Because I do feel like this is an important thing to go over, and I've only talked with one of you about this, so sorry if I'm repeating myself a bit. So here's a block, and here's a bullet. The mass is equal to 0.01 kilograms. I don't know the velocity. Now the bullet's probably going really fast. The bullet hits the block and it gets embedded in the block. It gets lodged in it. Now the block is tied to a string, and the block is going to go flying upwards, and it goes all the way up here to a maximum height, or at least it goes up, bless you, to a height of 2 meters. And the block weighs 10 kilograms, the bullet weighs 0.01 kilograms, and that's everything. So for these problems, you want to break it up. So in one of my energy video, I had one thing where I go time 1, time 2, time 3, time 4. You really want to do that for these energy problems. Yes, this is a momentum problem, but it's also an energy problem. It's hard to say which one it is because it just includes everything. So this is time 1, this is time 2, and this is time 3. At time, the bullet's moving, boom, it hits the block, it gets lodged into it. Now, first of all, this is a collision, so we just want to analyze the crap out of this. This is a collision. When things stick together, what type of collision is it? Inelastic. Inelastic is we're losing energy. So where do I have more energy? Here, or when this thing is moving to the right here? The left side. So yeah, we have heat energy, we have energy loss. So they could ask, how much energy did you lose? That's something they could ask. Now the block is moving to the right. Also, what type of energy is this? Kinetic energy. So I have kinetic energy. What type of energy is this? Still just kinetic energy. You can, if it's just hanging, the height here is 0, essentially. So it's again kinetic energy, less than this. And what type of energy is it here at its max height? It's all potential. So this is gravitational potential energy. How do the energies of times 2 and 3 compare with one another? They're the exact same. There is no work done. This is technically work of friction, energy lost. There's no work done here. It's complete completely equal to one another. So this is 1/2 the mass, and the mass is not 10. The mass is 10.01 because they stuck together. Times our velocity squared. I don't know the velocity. This is equal to the gravitational potential energy. The height of 2 times 9.8 times 10.01. Well, these cancel, and this cancels, and I can solve for this. 2 times 19.6, square root of that, 6.26. Velocity equals 6.26 meters per second. That's how fast this block and the bullet move together. Now, they easily could have asked this question differently. Maybe the bullet ricocheted off. That doesn't necessarily mean it's elastic, but we don't know if it's elastic or not, if it ricochets off. It's definitely inelastic if they stick together. Yeah, okay, so yeah, they just happened to stick together. They didn't have to. You would still do a conservation of momentum here in any case, which is actually where I'm going right now. So this, boom, kinetic energy transferred to potential energy, we solve for the velocity. Well here, yes, I lost some energy, but more importantly, it's a collision. So the kinetic energies are not the same. This kinetic energy is smaller than this kinetic energy, but the momentum before is equal to the momentum after. And the momentum for is just 0.01 times the unknown velocity of the bullet, which is equal to 10.01, because they're lodged together, times some velocity, which we solved for, right? So if you had gone from left to right in solving this, you would have realized, I don't know the velocity, and then you would have gone the other direction. So usually you just sweep one direction or the other direction. Whatever variable you don't have, probably start from the other direction. So 10.01 times our velocity, 6.626 times 10.01, and divide by 0.01, and the velocity is 6.267. Really fast bullet, 6,267 meters per second. There's a ridiculous number of variations of this problem. This was just one that came into my head. I could easily do 5 more. There's plenty of them in the book. Again, Adler is going to distort it a little bit so it's not so numbery, but all of the theory, all of the information is the same. Sometimes they ask about the height of this or the angle here, things like that. Yes?
When you're doing this momentum and you're doing the momentum before and momentum after, the momentum after, it's always the two masses, you add them together?
Only if it says that the language will be important. They get embedded, it gets stuck in, it gets lodged in.
So if it was like 2 wrestlers, you wouldn't?
If it was what?
Like 2 wrestlers hitting each other?
Well, no, wrestlers probably the same. I used to wrestle, and you grab onto a guy and you tackle him, like football players.
So that is together. Okay.
You'll have, they'll be more specific than expecting you to have an extensive knowledge of sports. They'll say one wrestler locks arm around the other wrestler, or
So
holds him. Yes, and here they say lodged, they say embedded. If they say ricochet, which is a popular term, that means the bullet bounced back this way, in which case it's MV equals MV plus MV. And one of these V's is probably negative if it's ricocheting backwards. So the details can vary, but it's still going to be a conservation of momentum here. It just depends, is it momentum, is it mass combined times velocity, or is it mass of bullet times new velocity plus mass of block times new velocity, and all of that depends. They're not going to give you so many details. And this here is this is only for conservation of inelastic collision problems. If you deal with the kinetic energy conservation problem, which I haven't seen any yet, but mastering physics sucks. So if you don't come across any kinetic energy collision problems, great, don't forget about it. If you do, this equation is going to be very, very, very helpful in letting you, because collisions that are elastic will have 2 variables usually, and to do that, you then need to do a conservation of kinetic energy to get the other set of 2 variables, and then you need to plug one set into the other set, and it's a nightmare. So usually what I recommend is if you do a kinetic energy, like an elastic collision problem, you're going to write the conservation of momentum. You're going to realize there's 2 variables, and then you just use this nifty equation that can allow you to solve for one of the variables and then plug it in. We don't have time to do one. They might not even do it, but just know that formula. And here it is for all of the people in TV land. That is the formula. Okay, and then I gotta get to see the other guy.